Quantum mechanics is the most precisely tested theory in the history of science, accurate to more decimal places than any framework humans have ever constructed, and yet the physicists who use it every day cannot agree on what it is actually describing. This is not a minor disagreement about technical details buried somewhere in the advanced literature. It is a foundational confusion sitting at the very center of the theory, visible to anyone willing to look directly at it, acknowledged in private by the physicists who built their careers on the equations. The theory predicts the outcomes of experiments with a precision that has no parallel in all of human intellectual history. It also has no agreed-upon explanation for what those predictions mean about the physical world. Consider what precision means here. Quantum electrodynamics, one branch of the quantum mechanical framework, predicts the magnetic moment of the electron to 11 significant figures. The experimental measurement agrees. The gap between theory and observation is smaller than the width of a human hair compared to the distance from New York to Los Angeles. No other scientific theory in any field, across all of recorded history, has ever achieved anything remotely close to this level of agreement between mathematics and measurement. Quantum mechanics is not approximately correct. It is correct in a way that seems almost unreasonable, as if the universe were deliberately confirming the equations. And yet, ask three quantum physicists what actually happens when a measurement is performed on a quantum system, what physically occurs in that moment when a superposition of possibilities resolves into a single definite outcome, and you will receive three entirely different answers. Not three variations on a shared theme. Three genuinely incompatible descriptions of reality, each held with complete conviction, each internally consistent, each contradicted by the others. This happened publicly at the World Science Festival in 2024, when leading researchers were asked precisely this question. The answers diverged completely. The audience watched physicists who had devoted their lives to the same theory describe fundamentally different pictures of what that theory says about the world. This state of affairs is, when examined directly, one of the strangest facts in all of science. Imagine if chemists disagreed about whether atoms existed. Imagine if structural engineers held incompatible beliefs about whether forces were real. In quantum mechanics, the situation is more extreme than either of those analogies suggests, because the disagreement is not about something peripheral. It is about what the theory is describing at every moment it is being used. Every calculation a quantum physicist performs rests on mathematical machinery whose physical interpretation remains genuinely contested after more than a century of the most intense scientific scrutiny the world has ever seen. The equations work. What they mean remains open. The practical response to this situation, developed gradually across the mid-20th century, was a professional culture of deliberate avoidance. If the theory produces correct predictions, calculate with the theory and stop asking what the theory means. This attitude, sometimes called shut up and calculate, was never formally adopted but became the effective standard across physics departments and research programs worldwide. It served a purpose. It allowed physics to advance at extraordinary speed, building transistors, lasers, and eventually the entire technological infrastructure of modern civilization, without stopping to resolve questions that seem to have no clean experimental handle. But avoidance is not resolution, and the questions that were set aside did not disappear. They accumulated, and at the foundation of all of them, deeper than the debates about interpretation and more fundamental than any of the competing philosophical positions, sits a single precise and devastating problem. A quantum system left alone evolves in one way. The moment it is measured, something else happens, something the theory describes with a completely different mathematical rule, something the theory cannot explain from within its own formalism. That rupture, that place where two incompatible descriptions of reality meet at the moment of observation, is called the measurement problem. And the strange thing is, most physicists already know this. They just learned, somewhere along the way, to stop asking. Left entirely to itself, a quantum system evolves in a perfectly predictable way, spreading through every possible configuration simultaneously, following the Schrödinger equation like clockwork. This is not a vague metaphor or a loose description of uncertainty. It is precisely what the mathematics demands. An electron traveling toward a detector does not take one path. It takes every path simultaneously, each weighted by a probability amplitude, the entire collection of possibilities evolving forward in time according to a single deterministic equation. This state is called a superposition, and in the absence of any measurement, it is the complete and total description of the system. Nothing is hidden, nothing is waiting to be revealed. The electron genuinely occupies multiple configurations at once, and the Schrödinger equation governs how that distribution shifts and spreads through time with absolute mathematical precision. Then something happens. A detector clicks. A photographic plate registers a mark. A physicist glances at a dial, and in that instant, the superposition vanishes. Every possible configuration the system had been inhabiting simultaneously collapses into a single definite outcome. The electron does not arrive at two positions. It arrives at one. The probability amplitudes that had been spreading through space simply stop, and a single result is left standing. This process is called wave function collapse, and it is where quantum mechanics breaks down as a coherent description of nature. Not breaks down in the sense of giving wrong predictions. It continues to give correct predictions with unnerving accuracy. It breaks down in the sense that the theory provides no account of what actually happened. The Schrödinger equation does not describe collapse. It does not predict when collapse occurs, what triggers it, or what physical process replaces a superposition with a single outcome. The equation that governs quantum systems simply does not contain this event. Collapse is added to the theory as a separate rule, appended by hand, with no derivation and no underlying mechanism. Consider what this means. Quantum mechanics operates according to two entirely distinct sets of rules, applied in two entirely distinct circumstances. When a system is left alone, the Schrödinger equation governs its evolution: deterministic, linear, continuous, reversible. When a system is measured, a completely different process takes over: stochastic, nonlinear, discontinuous, irreversible. There is no equation describing the transition between these two regimes. There is no definition within the theory of what constitutes a measurement, what qualifies as an observer, or at what scale the first set of rules gives way to the second. The boundary between quantum evolution and classical measurement is drawn by convention, not by mathematics, and different physicists draw it in different places. This is not a minor technical gap waiting to be filled. It is a logical rupture running through the foundation of the entire framework. What makes the problem sharper is that the Schrödinger equation, applied consistently, never actually produces a single outcome. Follow the mathematics without invoking the collapse rule, and what you get is a superposition that grows larger rather than smaller as the system interacts with a measuring device. The electron enters the detector in a superposition of positions. The detector's pointer moves into a superposition of readings. The physicist's retina receives a superposition of light patterns. The physicist's brain enters a superposition of mental states corresponding to different results. There is no stage at which the formalism selects one branch and discards the others. The wave function simply continues to evolve, branching outward through every possible outcome simultaneously, until something external to the mathematics is invoked to explain why only one of those branches is ever experienced. That external something is the collapse postulate, and it remains, after nearly a century, completely unexplained. Physicists have been aware of this problem since the earliest days of the theory. The response, for most of that century, has been to note that the predictions work and move forward. The Born rule, the mathematical relationship that converts probability amplitudes into the probabilities of specific measurement outcomes, gives correct answers with breathtaking consistency. The predictions of quantum mechanics have been tested against experiment to more decimal places than any other physical theory in history. Every test confirms the formalism, and yet the formalism, interpreted literally, describes a universe in which measurements have no definite outcomes, in which every possible result of every quantum event continues to exist simultaneously, accumulating in a perpetually expanding our position of unrealized possibilities. That is what the mathematics says. The Born rule then tells you how to calculate which outcome you will probably observe without explaining why you observe any single outcome at all. So, the universe appears, from within quantum mechanics, to behave according to entirely different principles depending on whether it is being observed. Unobserved, it evolves as a smooth deterministic wave, spreading through possibility. Observed, it snaps into a single definite state as though the wave function never existed. No theory in the history of science has contained this kind of internal division at its most fundamental level. a description of reality that changes its own rules based on the presence or absence of an observer, without explaining what an observer is, without specifying when observation begins or ends, and without providing any mechanism by which the transition occurs. The question is not whether this should trouble us. The question is how it has been possible to build the most successful predictive framework in the history of science on top of a foundation with this specific crack running through its center. The theory that describes atoms with extraordinary precision contains, at its very center, a description of reality that contradicts itself depending on whether anyone is watching. In 1935, Erwin Schrödinger designed a thought experiment specifically to show that the dominant interpretation of quantum mechanics was absurd. He was not playing a game. Schrödinger was one of the founding architects of quantum theory, the man whose equation describes how quantum systems evolve through time, and he found the conclusions his colleagues were drawing from that equation genuinely troubling. The Copenhagen Interpretation, developed primarily by Niels Bohr and Werner Heisenberg, held that a quantum system exists in a superposition of all possible states until a measurement forces it into one definite outcome. Schrödinger understood this perfectly well. What he wanted to demonstrate was what that claim actually implies when you follow it all the way up from the scale of electrons into the world of ordinary experience, where cats either breathe or they do not. The setup is deceptively simple. Imagine a sealed box. Inside the box sits a cat, a small radioactive atom, a Geiger counter connected to a mechanism, and a sealed vial of poison. The radioactive atom has exactly a 50% chance of decaying within 1 hour. If the Geiger counter detects a decay event, the mechanism shatters the vial, the poison is released, and the cat dies. If no decay occurs, the vial remains intact and the cat lives. After 1 hour, before anyone opens the box, what is the state of the cat? According to the Copenhagen Interpretation, the radioactive atom has not decayed or failed to decay. It exists in a quantum superposition of both possibilities simultaneously. The Geiger counter has both triggered and not triggered. The vial has both shattered and remained whole. And the cat, following this logic all the way to its conclusion, is simultaneously alive and dead, suspended in a superposition of both states until the moment someone opens the box and observes the outcome. At that moment, and not before, reality resolves into one definite state. Schrödinger found this conclusion monstrous. His entire point was that it cannot be right. A cat is not an electron. A cat is a macroscopic object with a definite biological state at every moment. Its heart either beats or it does not. Its neurons either fire or they do not. Its cells either metabolize or they have stopped. The idea that an act of human observation at the box's lid could be causally responsible for determining whether an animal is alive represents, in Schrödinger's view, a reductio ad absurdum of the Copenhagen position. He was not proposing the superposition of a cat as a fascinating possibility. He was holding it up as evidence that something had gone badly wrong in the interpretation of the theory. What made this more than a philosophical complaint was its precision. The chain of physical connections between the radioactive atom and the cat is entirely continuous. Each link in the sequence is just more physics, the same physics that Copenhagen applies to electrons, applied step by step to progressively larger systems until it produces a conclusion that strikes every human being with functioning intuitions as obviously impossible. There is no principled place in the chain to draw a line and say quantum rules apply here but not there. Bohr's interpretation demanded such a line but did not specify where it ran or what physical property determined its location. Schrödinger saw this as an admission that the interpretation was incomplete in a way that mattered deeply. The cat thought experiment has been absorbed into popular culture as a charming illustration of quantum strangeness, which is almost exactly the opposite of what Schrödinger intended. It appears on t-shirts and in casual conversation as a symbol of quantum weirdness to be celebrated. In its original context, it was a physicist of the first rank declaring that a physical theory he helped create was being interpreted in a way that produced absurdities, and that the absurdities were being treated as profound insights rather than symptoms of a problem demanding a solution. The distinction matters because the problem Schrödinger identified in 1935 was real and has never been adequately answered. Physicists have proposed many responses to it in the decades since, responses that will occupy much of what follows, but none of them has achieved anything approaching consensus. and none has dissolved the underlying tension that Schrödinger put his finger on with a sealed box and an unfortunate cat. 90 years later, the box is still sealed, the cat's fate is still officially undetermined, and the argument Schrödinger started has never actually been resolved. Niels Bohr's answer to the measurement problem was not a gap in the theory, it was a deliberate and radical philosophical position. Where Schrödinger saw absurdity, Bohr saw clarity. The Copenhagen Interpretation, developed through years of argument between Bohr and Werner Heisenberg in the late 1920s, does not evade the question of what happens during a measurement. It answers the question directly, and the answer is more unsettling than most physicists who use it daily are willing to acknowledge. The claim is this: physical properties do not exist until they are measured. Not hidden, not uncertain, not merely unknown, non-existent. An electron does not have a position while it travels from one place to another. It does not have a definite spin while nothing is interacting with it. Momentum is not a property waiting to be discovered. It is a property that does not come into being until an act of measurement forces it into reality. This is not a statement about the limits of human knowledge. It is a statement about the structure of nature itself. Bohr insisted that the question, "Where was the electron before we measured it?" is not a question that has a well-formed answer, and demanding one reflects a misunderstanding of what quantum mechanics is describing. The principle Bohr placed at the center of Copenhagen was complementarity. Certain pairs of physical properties, position and momentum, energy and time, are not simultaneously real. Ask where something is, and it becomes meaningful to speak of its location. Ask how fast it is moving, and that becomes the quantity that has meaning. Attempt to ask both questions at once, and the theory does not return an uncertain answer. It returns the instruction that both questions cannot apply simultaneously to the same physical system. This is what the uncertainty principle actually means under the Copenhagen interpretation. Not that measurements disturb each other in a mechanical sense, but that the properties themselves cannot simultaneously exist. Heisenberg's original derivation suggested the disturbance picture, but Bohr's deeper framework replaced it with something more radical. Complementary descriptions are mutually exclusive features of reality, not merely of our instruments. Consider what this demands. A particle traveling through a double-slit apparatus does not pass through the left slit or the right slit before any detection is made. It has no definite path. The interference pattern that appears on the screen is not the result of two possible paths somehow combining. It is the result of a system that had no path at all until the screen registered a detection. The formalism that produces this result is perfectly correct. The interpretation of that formalism is that path is not a property the particle carried through the experiment. Copenhagen requires accepting this statement at face value without seeking a deeper level of description where the path was hiding all along. Albert Einstein found this conclusion philosophically unbearable. He spent years constructing arguments against it, insisting that the Copenhagen interpretation was simply incomplete rather than correct. His most famous expression of this resistance came in a conversation with the physicist Abraham Pais, during which Einstein stopped walking and asked whether Pais genuinely believed the moon exists only when someone looks at it. The question was not a joke. Einstein was identifying the point at which Copenhagen's logic, applied consistently, seemed to reach results that no reasonable picture of the world could accommodate. If a particle has no position before measurement, and if the moon is composed of particles, then what is the moon doing when no one is observing it? Bohr's answer, essentially, was that this question is not well posed, that the classical concept of an object with definite properties existing independently of any measurement context simply does not apply at the quantum level, and extending it to moons is an assumption that physics does not require us to make. What is remarkable is how thoroughly mainstream physics absorbed the operational core of Copenhagen, use the wave function, apply the Born rule, get the probabilities, do not ask what is happening between measurements, while quietly setting aside the philosophical implications. The textbooks teach the formalism. They rarely teach what Bohr actually believed the formalism meant. Generations of physicists learned to extract predictions from quantum mechanics without being asked to confront the interpretation's central assertion that there is no observer-independent reality at the quantum level, that physical properties are not features of objects but features of interactions between objects and measuring devices, and that asking what a system is doing when it is not being measured is a category error rather than an unanswered question. Bohr was not confused about what the Copenhagen interpretation implied about reality. He simply thought the implications were correct, and he was willing to follow them wherever they led. In 1935, the same year Schrödinger published his cat, Albert Einstein co-authored a paper arguing that quantum mechanics, taken at face value, was simply unfinished. Einstein's collaborators were Boris Podolsky and Nathan Rosen, and together the three men constructed an argument designed not to replace quantum mechanics, but to expose what they believed was a fundamental gap at its core. The paper is remembered today by their initials, EPR. It remains one of the most consequential documents in the history of physics, not because it was correct in every detail, but because the question it asked has never entirely gone away. The argument begins with a concept that quantum mechanics itself predicts, and that experiment has confirmed in extraordinary detail: entanglement. Two particles can interact in such a way that their quantum states become correlated, and this correlation persists no matter how far apart the particles subsequently travel. Measure the spin of one particle along a given axis, and you instantly know the spin of the other particle along that same axis, regardless of whether the second particle is across the room or across the galaxy. Quantum mechanics does not merely suggest this, it demands it, and it has been verified in laboratory conditions with increasing precision for decades. Einstein found this deeply troubling, and his reasoning was precise. Consider two particles that have interacted and then separated by an enormous distance. An experimenter measures the first particle and obtains a definite result. At that exact moment, the second particle's corresponding property is determined. Either something has traveled between the two particles instantaneously, connecting them across arbitrary distances in violation of everything relativity requires, or the second particle had a definite value for that property all along and the measurement simply revealed it. There was no third option that Einstein could accept. Faster-than-light influence struck him as physically impossible. Therefore, the second particle must have carried that property with it from the beginning, encoded in what the EPR paper called elements of reality. Here is where the argument becomes an attack on Copenhagen directly. If the second particle already had a definite spin before anyone measured it, then the quantum mechanical wave function, which assigns only probabilities to outcomes before measurement, is not telling the complete story. It is a description of our knowledge, not of the underlying physical situation. Hidden somewhere beneath the probabilistic surface of quantum mechanics, Einstein insisted, must be a deeper level of description where particles have definite properties, where measurement reveals rather than creates, and where nothing influences anything else faster than light. The incompleteness of quantum mechanics was not a failure of ingenuity, but a logical necessity forced by the demand that physics describe a reality that exists independently of observation. This is what physicists mean when they speak of local realism, and Einstein held it with the conviction of a first principle. Locality means that distant objects cannot directly influence each other instantaneously. Any physical influence must propagate through space at or below the speed of light. Realism means that physical properties exist independently of measurement, that the moon does not require an observer to possess a definite position in space. Einstein famously pressed this point in conversation with Bohr, asking whether the moon ceased to exist when no one was looking at it, a question Bohr reportedly found more difficult to answer than it appears. For Einstein, local realism was not a philosophical preference but the minimal requirement for physics to be a coherent enterprise. At all. Bohr disagreed, and the disagreement was not a matter of emphasis or interpretation. Bohr genuinely believed that the EPR argument failed because the two particles and the measuring apparatus must be treated as a single undivided system rather than as separate objects with independent properties. The act of measuring one particle is not separable from the experimental context in which the second particle exists. Asking about the second particle's spin before any measurement has been performed is, in Bohr's view, a question without physical meaning. Properties do not exist independently of the experimental conditions designed to measure them. Bohr accepted this conclusion with equanimity. Einstein found it a capitulation to confusion dressed up as philosophy. What makes the EPR argument historically remarkable is how thoroughly Einstein's physical intuitions had carried physics for 3 decades before this point. The special theory of relativity, the general theory, the photoelectric effect, Brownian motion, the record was extraordinary. And yet on this question, the community of physicists largely sided with Bohr, not because EPR had been refuted experimentally at that stage, but because quantum mechanics continued to produce correct predictions while Einstein's program of finding hidden variables produced nothing. The argument remained alive but unresolved, a dispute between two visions of what a physical theory is supposed to accomplish, sustained by philosophical conviction on both sides and by the absence of any experimental test capable of deciding between them. That experimental test would eventually come, though Einstein did not live to see it. The question he posed in 1935, whether quantum mechanics was incomplete or whether local realism was simply wrong, turned out to be answerable, and the answer was not the one he wanted. Einstein believed the universe was ultimately a sensible place with definite properties that existed whether or not anyone was looking, and he spent the last 20 years of his life unable to prove it. In 1964, a physicist named John Bell found a way to turn an argument about the philosophy of physics into a testable prediction about the physical world. This was not a small achievement. The dispute between Einstein and the Copenhagen Interpretation had been running for nearly 30 years by that point, and the general consensus among working physicists was that it would remain forever in the realm of interpretation, a matter of philosophical preference rather than experimental fact. Bell disagreed. He saw that hidden beneath the abstract arguments about local realism and completeness, there was a concrete mathematical claim, and that concrete mathematical claims could, in principle, be tested against the actual behavior of matter. What Bell did was construct an inequality, a precise numerical boundary that any hidden variable theory of the local kind was mathematically required to obey. The logic behind Bell's inequality is exact and unsparing. If particles carry predetermined hidden properties that determine how they will respond to any measurement, as Einstein's vision of local realism demanded, then the correlations observed between measurements on separated particles cannot exceed a certain strength. Bell calculated exactly what that strength was. The correlation coefficients between outcomes measured along different angles cannot, under any local hidden variable theory, violate a specific numerical bound. Quantum mechanics, by contrast, predicted correlations that exceeded this bound by a calculable amount for certain measurement configurations. The two competing pictures of reality were no longer merely philosophically distinct. They made different quantitative predictions about numbers that could be read from instruments. So, consider what this represented. The EPR argument had essentially been a dispute about which framework better captured the deep structure of reality, and such disputes tend to dissolve into irresolvable disagreement about what words like real and complete are supposed to mean. Bell transformed this into a question with a numerical answer. Either nature's correlations stay within the classical boundary or they exceed it. The universe itself would have to declare which vision was correct. Prepare yourselves. This is the moment where philosophy ended and measurement began. The first serious experimental tests came in the early 1970s, but the experiments that genuinely settled the question arrived with Alain Aspect and his collaborators at the Institut d'Optique in Paris in the early 1980s. Aspect's experiments used pairs of photons emitted from calcium atoms, their polarizations entangled in precisely the way Bell's theorem required for a meaningful test. Measurement settings were changed rapidly enough to prevent any signal traveling at the speed of light from carrying information between detectors before the measurements were completed. This closed what was known as the locality loophole, the possibility that the two detectors were somehow communicating classically and coordinating their results. The measured correlations exceeded Bell's bound by margins that were statistically definitive. The data didn't merely prefer quantum mechanics, it ruled out local hidden variables with overwhelming force. But here is where the mystery deepens. Even after Aspect's results, critics identified what became known as loopholes, not ways to restore local hidden variables, but ways to argue that the experiments hadn't been airtight enough to fully eliminate every conceivable classical explanation. The detection loophole exploited the fact that early experiments only detected a fraction of the photon pairs produced, raising the theoretical possibility that the detected subset was unrepresentative. The locality loophole, despite Aspect's precautions, was never completely sealed in those early experiments because the switching wasn't guaranteed to be random in the required sense. Physicists spent the following 3 decades designing progressively more rigorous versions of the test, closing each loop, hole in turn. The loophole-free Bell tests arrived in 2015, conducted independently by groups in Delft, Vienna, and Boulder, each using different physical systems and experimental architectures. All three found the same result. Nature violated Bell's inequality. Every single time. The implications deserve to be stated plainly rather than softened. Local realism, the principle that objects have definite properties independent of observation and that distant objects cannot influence each other faster than light, is incompatible with the observed behavior of the physical world. This is not a matter of interpretation. It is not a philosophical preference. It is an experimentally verified fact about nature with a precision that leaves no statistical room for doubt. Einstein's vision of an underlying reality populated by particles with predetermined hidden properties, a vision that felt to him like the only philosophically defensible picture of what physics should be describing, was eliminated by instruments and numbers. The universe does not work that way. Something genuinely non-local is occurring when entangled particles are measured, and the only remaining question is how to describe it correctly. What Bell's theorem did not do was tell physicists what to replace local realism with. The theorem closed a door but opened nothing specific behind it. Some physicists accept a weakened form of locality and abandon realism entirely, concluding that unmeasured properties simply don't exist, which returns them directly to Copenhagen. Others abandon locality while preserving a different kind of realism, concluding that entangled particles somehow influence each other across arbitrary distances, which creates its own severe tensions with the structure of special relativity. Still others embrace many worlds and claim the apparent non-locality dissolves when the full branching structure of the wave function is taken into account. None of these positions is obviously correct, and none of them is obviously wrong, which is perhaps the most unsettling outcome of all. That an experiment so definitive could leave so much unresolved. The experiments done, the inequality was violated, and the comfortable picture of a universe with hidden definite properties quietly died. The results stood, the implications were left unaddressed. Hugh Everett's solution to the measurement problem was to take the Schrödinger equation completely seriously and follow its implications all the way to the end. Every other interpretation had, at some point, introduced an additional rule, a collapse postulate, a special status for observers, a boundary between quantum and classical reality. Everett refused. If the Schrödinger equation describes everything that exists, then it describes measuring devices and scientists and the entire laboratory just as readily as it describes electrons and photons. And if that is true, then during a measurement, the equation does exactly what it always does. It evolves the entire system, observer included, into a superposition of every possible outcome simultaneously. There is no collapse. There was never any need for one. The proposal appeared in Everett's doctoral dissertation in 1957, and it was not well received. Niels Bohr dismissed it. Most of the physics community ignored it. Everett eventually left physics and spent his career working in operations research. But the idea did not die, and decades later, it experienced a serious revival among physicists who found the measurement problem impossible to escape by any other route. The framework is now called the Many Worlds Interpretation, a name Everett himself never used, and it commands genuine respect from a significant fraction of working physicists, including some who have spent entire careers studying the foundations of quantum mechanics. The core claim is this: when a physicist measures a quantum particle that is in superposition, the wave function does not collapse into one outcome. Instead, the entire universe, the particle, the detector, the physicist, everything, branches into multiple copies, each containing one of the possible outcomes. In one branch, the particle went left. In another branch, the particle went right. Both physicists are real. Both outcomes happened. Neither branch is more fundamental than the other, and neither physicist is aware of the other's existence, because quantum mechanics itself guarantees that the branches cannot interfere with each other once they have separated sufficiently. The experience of seeing one definite result is not because only one result occurred. It is because each copy of the observer lives in only one branch and has no access to the others. The mathematical appeal of this framework is genuine and should not be understated. There is no arbitrary collapse rule appended to the theory. There is no special category of events called measurements that require different treatment. There is no privileged role for observers or consciousness or classical measuring devices. The Schrödinger equation runs continuously and universally without exception. In the language of physics, this is called unitarity, and many theorists regard it as something close to sacred, a symmetry of the theory that every other interpretation casually discards every time a measurement occurs. Many worlds preserves it completely. The mathematical structure is clean in a way that no collapse-based interpretation can match, and that cleanliness has convinced serious physicists that the interpretation deserves to be taken seriously, regardless of how strange its implications become. But the implications are extraordinary. Consider how many quantum events occur every second in every cubic centimeter of matter throughout the observable universe. Every radioactive decay, every photon absorbed by an electron, every interaction at the subatomic level that has more than one possible outcome, each one branches the universe according to many worlds. The number of branching events since the Big Bang is not merely large, it is incomprehensible, and each branch is itself a complete universe containing everything. The proliferation is not just of parallel Earths, but of parallel everything, extending in all directions through time, spawning further branches continuously at a rate that makes any finite number seem inadequate to describe it. Everett's interpretation solves the measurement problem by accepting a cost that is difficult to fully hold in the mind. There is also a more technical problem that many worlds has never fully resolved, and it concerns probability. If every outcome of a quantum measurement actually occurs in some branch, then in what sense does it make sense to say that one outcome is more probable than another? Quantum mechanics assigns probabilities through the Born rule. The probability of each outcome is proportional to the squared amplitude of the corresponding part of the wave function. This rule works extraordinarily well in practice, matching experiment after experiment. But in many worlds, where all outcomes occur, the meaning of these probabilities is genuinely unclear. Why should an observer expect to find themselves in the high amplitude branch more often than the low amplitude branch if observers end up in Eve Rye branch? Various attempts have been made to derive the Born rule from within the many worlds framework, most notably through work involving decision theory and what is called the Deutsch-Wallace approach. But the question of whether these derivations actually succeed or merely restate the assumption they are trying to prove remains actively contested among physicists who specialize in exactly this question. The honest answer is that many worlds trades the inexplicability of collapse for the inexplicability of the branching itself and exchanges one observer-dependent mystery for an infinite multiplicity of observers who will never compare notes. Many worlds does not explain what happens during a measurement so much as it dissolves the question by insisting everything happens, which is either the most elegant solution in the history of physics or the most extravagant assumption ever made. Eugene Wigner imagined a scenario so simple that it seems like it should have an obvious answer, and the fact that quantum mechanics cannot provide one tells you more about the theory than 100 textbook derivations. The setup requires almost nothing. A physicist, call her the friend, is sealed inside a laboratory with a single quantum particle, a detector, and a notebook. She performs a measurement on the particle. According to everything quantum mechanics says about the measurement process, the wave function collapses. She records a definite outcome. From inside the laboratory, the experiment is finished, the result is written down, reality has resolved itself into one specific state. Wigner stands outside the sealed laboratory. He has not looked inside. He has not interacted with the particle, the detector, or the friend. From his position, the entire contents of the laboratory, the particle, the measuring device, the friend herself, including whatever she experienced and recorded, form a single composite quantum system, and that system has been evolving under the Schrödinger equation without interruption. No measurement has occurred from Wigner's perspective because no information has reached him. According to quantum mechanics, the laboratory and everything in it remains in superposition. The friend is in a superposition of having recorded two different outcomes. From outside, she has not yet seen anything definite at all. Both descriptions are internally consistent. Both follow directly from the rules of quantum mechanics applied carefully and correctly. The friend inside the laboratory assigns one wave function to her situation. Wigner outside the laboratory assigns a completely different wave function to the same physical situation. And quantum mechanics, as a mathematical framework, endorses both of them simultaneously. Consider what this actually requires you to believe. The friend had a real experience. She saw a number, wrote it down, perhaps felt a small satisfaction that the experiment worked. That experience is, from her perspective, as definite and concrete as anything that has ever happened to her. Wigner, applying the same theory to the same physical system, treats her entire experience as part of an unresolved superposition. Her memory, her written record, her conscious observation, all of it is suspended in quantum limbo from the outside perspective. The question of who is correct does not have an answer that quantum mechanics is willing to give. This is not a variant of the Schrödinger's cat problem, although the family resemblance is obvious. The cat was never an observer in any meaningful sense. It was an object whose fate was entangled with a quantum event. The friend is a physicist performing an experiment with full awareness of what she is doing. Wigner extended the paradox specifically to a conscious observer because the Copenhagen interpretation had placed enormous weight on the act of observation as the thing that collapses, wave functions, and produces definite outcomes. If the friend counts as an observer, her wave function should have collapsed. If she counts as a quantum system, it should not have. The theory provides no clean criterion for deciding which description applies, and the two descriptions lead to genuinely contradictory conclusions about what has happened in the world. The paradox sat comfortably as a thought experiment for decades, generating philosophical argument without any possibility of experimental resolution. The friend inside the laboratory cannot be interrogated without Wigner opening the door, which would itself constitute a measurement and collapse whatever superposition he had been maintaining, or so it seemed. In 2019, a team of researchers at Heriot-Watt University in Edinburgh constructed an experimental analog using entangled photons standing in for the observers, with optical elements acting as measurements, in a configuration designed to test whether the incompatible records predicted by the Wigner's friend scenario could actually be demonstrated in a physical system. The results confirmed that the two sides of the paradox produce genuinely incompatible measurement records, each internally consistent with the quantum mechanical description assigned to that observer, with no reconciliation available between them. What this implies is worth sitting with carefully. Physics has long operated on an assumption so basic that it rarely gets stated, that events either happen or they do not, that the outcomes of experiments are facts about the world that different observers can in principle agree on, that there is a shared objective reality underlying what we measure. The Wigner's friend paradox, taken seriously, suggests that quantum mechanics is incompatible with this assumption. Two observers can apply quantum mechanics correctly, in perfect accordance with every rule the theory provides, and arrive at mutually contradictory accounts of the same physical event. Neither account is wrong. The theory simply does not contain the machinery to tell you which one describes what actually happened, because it offers no answer to the question of whether there is a fact about what actually happened that both observers share. The experimental version of Wigner's friend, run in 2019, confirmed that quantum mechanics allows two observers to have incompatible but internally consistent records of the same physical event, which is either a profound result about the nature of reality or proof that something in the theory is deeply broken. The most popular answer to the measurement problem in modern physics is decoherence, and it explains almost everything except the part that actually matters. The argument runs as follows. No quantum system ever exists in perfect isolation. A particle moving through a laboratory is constantly bombarded by stray photons, air molecules, and thermal fluctuations, each interaction leaving a tiny imprint on the surrounding environment. These imprints are individually undetectable, but collectively they carry away the phase relationships between the different branches of a superposition, scrambling them across an astronomically large number of environmental particles. Once those phase relationships are gone, the interference effects that make quantum behavior visible disappear with them. The system stops behaving like a quantum superposition and starts behaving exactly like a classical object with a definite but unknown state. This process happens with extraordinary speed in warm, dense environments. For a large object at room temperature, decoherence occurs in something like 10 to the power of -23 seconds, which is so fast it is essentially instantaneous by any standard of measurement available to us. This is genuinely important physics. Decoherence explains why the quantum world and the classical world appear so sharply divided, despite being governed by the same underlying equations. It explains why cats and chairs and measuring devices do not visibly occupy superpositions of states, why quantum interference effects disappear as systems grow larger and more complex, and why the strange behavior confirmed in laboratory experiments with electrons and photons does not obviously extend to the objects of everyday experience. Before decoherence was fully understood, these questions had no rigorous answer within quantum theory itself. That changed substantially in the work of Wojciech Zurek, a physicist at Los Alamos National Laboratory who has spent decades developing the theoretical framework surrounding decoherence and pushing it towards something more complete. Zurek's contribution extends beyond standard decoherence into what he calls quantum Darwinism. The central idea is that the environment does not merely destroy quantum coherence, it selects. Of all the possible states a quantum system could occupy, only certain configurations survive repeated environmental interaction without being scrambled beyond recognition. These preferred states, which Zurek calls pointer states, are the ones that leave stable, redundant imprints across many different environmental subsystems simultaneously. A chair is in a definite location not because observation collapses its wave function in some mysterious act of measurement, but because its position state continuously imprints itself on surrounding photons, which carry that information outward in every direction. Multiple observers, sampling different fragments of the environment, all recover the same record of where the chair is. Classical objectivity, in this picture, is not a primitive feature of reality, but an emergent consequence of the way quantum systems interact with their surroundings. Consider what this framework accomplishes. It dissolves the need for a sharp boundary between quantum and classical domains, replaces the mysterious act of wave function collapse with ordinary quantum evolution involving a large number of particles, and explains why the world appears to have stable, definite properties that multiple observers can agree on. These are not small achievements. The decoherence program represents the most technically serious attempt to explain the classical world as a consequence of quantum mechanics rather than an assumption imported from outside it. Many physicists regard it as the essential framework within which any serious discussion of the measurement problem must now take place. But here is where the difficulty persists. Decoherence transforms a quantum superposition into something that is mathematically indistinguishable from a classical probability distribution, a list of possible outcomes with definite probabilities attached to each. The problem is that this mathematical equivalence is not the same as an actual definite outcome. After decoherence has done its work, the different branches of the superposition no longer interfere with each other and can be treated as if they were separate classical possibilities. What decoherence cannot do, and what Zurek has never claimed it can do, is explain why one branch becomes the actual outcome and the others do not. The wave function, spread across all branches, does not collapse under decoherence. It simply becomes a upper position in which the branches can no longer influence each other. The question of which branch is real, the question Schrödinger's cat made unavoidable, remains entirely open. Decoherence provides a rigorous account of why quantum systems stop looking quantum. It provides no account whatsoever of how a single definite reality is selected from among the branches that decoherence has rendered mutually invisible. After decoherence, the system no longer shows interference. It no longer looks quantum, but it is still technically in superposition. Decoherence tells you why the cat doesn't look like it's in both states, but it cannot tell you which state the cat is actually in. Girardi, Rimini, and Weber took a different approach to the measurement problem than everyone else. Instead of reinterpreting quantum mechanics, they simply changed the equations. Every other response to the measurement problem had accepted the Schrödinger equation as correct and argued about what it meant. Copenhagen said measurement creates reality. Many worlds said every outcome happens somewhere. Decoherence said the environment scrambles the superposition into something that merely resembles a classical outcome. All of these are interpretations. They leave the mathematics untouched and argue about the philosophy surrounding it. GRW, the theory published by Giancarlo Girardi, Alberto Rimini, and Tullio Weber in 1986, did something far more radical. It proposed that the Schrödinger equation is simply not the complete story, that the actual evolution of quantum systems includes an additional physical process. The standard formalism had been missing entirely. The additional process is a spontaneous, random localization, a collapse that occurs without any observer, without any measurement apparatus, without any interaction of the kind quantum mechanics traditionally identifies as a measurement event. At random moments, governed by a tiny probability per unit time, any given particle in the universe undergoes a sudden localization to a specific region of space. The wave function doesn't spread indefinitely following the Schrödinger equation. It gets hit, as the technical literature calls it, and snaps to a definite location. This process is entirely physical. Nothing is watching. No conscious observer is required. The collapse happens because the universe contains a physical mechanism that produces it, not because a human opened a box. The numbers involved are extreme in both directions, and that is precisely the point. For a single electron, the collapse rate in the original GRW model is approximately once every 100 million years. For any practical purpose involving individual particles, the wave function evolves exactly as the standard Schrödinger equation predicts. The spontaneous localization is so rare that it contributes nothing detectable to any experiment sensitive only to single particles. This is why GRW makes essentially the same predictions as standard quantum mechanics in all the situations where standard quantum mechanics has been tested. The theory is deliberately constructed to be invisible at the scale where quantum superposition is observed. But consider what happens when the system grows larger. A cat contains on the order of 10 to the power of 27 particles, each carrying its own collapse probability. The combined effect of trillions upon trillions of independent localization events means the entire system collapses to a definite state in an interval so short it is effectively instantaneous. There is no need for an observer, no need for an environment of the kind decoherence requires, no need for any additional interpretation. The macroscopic world appears classical not because of what we do to it, but because of what the universe does to it, continuously, on timescales far shorter than any measurement we could perform. Schrödinger's cat is not in superposition because the physical collapse mechanism resolves it ln g before the box is ever opened. The appeal of this is genuine and should not be dismissed. GRW is a real scientific theory in the sense that matters most. It makes predictions that differ, in principle, from standard quantum mechanics. If collapse rates were somewhat higher than the original parameters assumed, or if localization produced detectable signatures in systems of intermediate size, experiments could in principle rule it out. Several ongoing experimental programs are searching precisely for these signatures, testing whether matter at mesoscopic scales, larger than a single particle but smaller than a cat, behaves exactly as standard quantum mechanics predicts or shows subtle deviations consistent with some form of objective collapse. The theory is falsifiable, which places it on firmer scientific ground than interpretations that make identical predictions by construction. The cost, however, is substantial. GRW introduces two new fundamental constants into physics, a collapse rate and a localization width, whose values are chosen to reproduce our observations of quantum and classical behavior, but derive from no deeper principle. There is no equation from which these constants emerge, no symmetry that fixes their values, no theoretical argument that explains why nature should have chosen them rather than any other numbers. They are fitted to the data the way epicycles were fitted to planetary motion before Kepler. They work, and the reason they work is simply that they were selected to work. Additionally, the original GRW formulation is non-relativistic, meaning it is fundamentally incompatible with special relativity. Relativistic extensions have been attempted, but none has achieved the same conceptual cleanliness as the original theory, and compatibility with quantum field theory remains an open problem. The GRW theory solves the measurement problem cleanly and completely, and it does so by proposing the existence of physical processes that have never been detected, described by constants pulled from no deeper principle, which is either a modest price to pay or a sign that something important is being papered over. The measurement problem would be troubling enough on its own, but quantum mechanics carries a second wound that cuts even deeper. It is fundamentally incompatible with the other theory physicists rely on to describe the universe. General relativity is the theory of gravity, of spacetime, of the large-scale architecture of the cosmos. It has been confirmed to extraordinary precision, the bending of light around massive objects, the precise advance of Mercury's perihelion, the gravitational waves detected in 2015 rippling outward from colliding black holes exactly as the equations predicted. It is, by any reasonable measure, one of the greatest intellectual achievements in human history. Quantum mechanics is the other pillar, governing every atom, every photon, every interaction at the subatomic scale, confirmed to more decimal places of precision than any framework physicists have ever built. And these two theories, each verified beyond any reasonable doubt within its own domain, fundamentally cannot be reconciled with each other, not in some minor technical sense, not in a way that better engineering will eventually solve. They are built upon assumptions about the nature of reality that are mutually exclusive at the most basic level. So, general relativity describes gravity as the smooth curvature of space-time itself, a continuous geometric structure that bends and warps in response to the presence of mass and energy. The key word is continuous. Space-time in general relativity is a seamless fabric, infinitely divisible, with no smallest unit, no graininess at any scale. Quantum mechanics describes everything else: electromagnetism, the strong and weak nuclear forces, through quantized fields, meaning fields that come in discrete packets, granular and probabilistic, fundamentally discontinuous at small scales. When physicists attempt to apply the same quantization procedure to gravity, the mathematics collapses into nonsense. The equations begin producing infinities, infinite energies, infinite probabilities, and unlike the infinities that appear in other quantum field theories, these ones cannot be removed by any known mathematical technique. This process, called renormalization, rescued quantum electrodynamics and the other quantum field theories from similar problems, but gravity defeats it. The infinities in quantum gravity do not cancel, they proliferate. Consider what this actually means. Every other known force has been successfully described within the quantum framework. Electromagnetism became quantum electrodynamics. The strong nuclear force became quantum chromodynamics. The weak force was unified with electromagnetism into the electroweak theory. Gravity alone resists. It is the oldest known force, the one that governs every object you have ever seen with your own eyes, and it is the only fundamental force that has never been successfully incorporated into quantum mechanics. Physicists have known this for roughly a century, and the problem has not been solved. The incompatibility runs deeper than the mathematics. The two theories are built on contradictory assumptions about locality and the structure of physical description itself. General relativity is a local theory. What happens at any given point in space-time depends only on the conditions immediately surrounding that point, encoded in the smooth curvature of the geometry. Quantum mechanics, as Bell's theorem made unavoidably clear, is in some essential sense non-local. The correlations between distant entangled particles cannot be explained by any locally realistic model. A geometric theory of smooth local space-time curvature and a theory requiring some form of non-local quantum correlation are pointing at incompatible pictures of what the world is made of. Any theory that successfully unified them would have to resolve this conflict, which means one or both of our current pictures must be fundamentally incomplete or simply wrong at some level we have not yet identified. The region where this conflict becomes physically acute is not accessible to current experiments. It lies at the Planck scale, distances of roughly 10 to the power of negative 35 meters, energies so extreme they existed only in the first moments after the Big Bang, and inside the singularities that general relativity predicts at the centers of black holes. At those scales, both quantum mechanics and general relativity must apply simultaneously, and they produce irreconcilable descriptions. General relativity predicts a definite space-time geometry. Quantum mechanics implies that geometry should itself be subject to quantum fluctuations, uncertain and superposed. What space-time is doing at the Planck scale is genuinely unknown because no theoretical framework exists that can answer the question coherently. Two research programs have spent decades attempting to bridge this gap. String theory replaced point particles with one-dimensional vibrating strings, eliminating the infinities by spreading interactions over a finite-length scale, and in doing so produced a framework that appeared to unify quantum mechanics with gravity in a mathematically consistent way. Loop quantum gravity took a different approach, quantizing space-time geometry itself, proposing that space is not continuous but woven from discrete quantum units at the Planck scale. Both programs have attracted some of the most talented theoretical physicists alive. Both have generated enormous mathematical structures of considerable internal beauty. What neither has generated is a confirmed experimental prediction, a specific testable consequence that distinguishes the theory from existing physics and that experiment has actually verified. After decades of effort, the theoretical machinery of quantum gravity remains disconnected from anything that can be measured in a laboratory or observed in the sky. This is not an ordinary gap in scientific knowledge of the kind that patience and funding will eventually close. It reflects something genuinely alarming about the current state of fundamental physics. The two theories that underlie all of modern science, that between them describe every phenomenon from the interior of a proton to the expansion of the universe, were never compatible to begin with, and the effort to make them compatible has so far produced no physics that can be tested against the world. String theory has been under active development since the 1980s, loop quantum gravity even longer, and neither has produced a confirmed experimental prediction. The two great pillars of modern physics still cannot be made to occupy the same building. After Bell's theorem and the experiments that confirmed it, physicists were left with a fact about the universe that no interpretation of quantum mechanics has made comfortable. Measuring one particle of an entangled pair instantaneously determines the outcome of measuring the other, no matter how far apart they are. Consider what that distance actually means. Two particles, entangled in a laboratory, can be separated by any amount, across a room, across a continent, across the observable universe, and the correlation holds. The moment one particle's spin is measured as up, its partner is down instantaneously with no signal traveling between them, no mechanism visible in the equations that could account for the connection. This is not a theoretical prediction awaiting confirmation. It has been tested to extraordinary precision in experiments carefully designed to close every possible loophole, and the result is always the same. The correlation is real. The non-locality is real. The universe does not care about the distance. What makes this genuinely difficult is that it isn't simply a curiosity. It cuts directly into the conceptual architecture of physics. General relativity is built on a principle called locality, the principle that an event at one location can only influence events at nearby locations, and that influence propagates outward at the speed of light or slower. Nothing in general relativity permits instantaneous influence across arbitrary distances. The geometry of space-time, the curvature that produces gravity, the causal structure that prevents effects from preceding their causes, all of it rests on this foundational assumption. Quantum entanglement appears to violate it. The standard response to this is to point out that entanglement cannot be used to send information faster than light. Measuring one particle does not let you choose what outcome you get. The results look random locally, and only when you compare measurements through ordinary classical communication does the correlation become visible. So no message travels faster than light, and relativity's prohibition on faster than light signaling is technically preserved. This answer satisfies most working physicists. It has never fully satisfied anyone who pressed on what is actually happening, because something is happening. The particles are correlated in a way that no local explanation can account for. Bell proved this, and the experiments confirmed it. If no signal passes between them, and they were not carrying hidden instructions from the moment they were created, then the only remaining description is that they are not, in the relevant sense, separate things at all. Their states are defined not locally, but relationally, across whatever distance separates them, as though space between them were not quite the barrier it appears to be. This is the problem that no comfortable language has resolved. The tension between quantum non-locality and relativistic locality runs deeper than a technical incompatibility between two sets of equations. These two frameworks disagree about the fundamental structure of reality at the level of what separates one thing from another. General relativity is formulated in space-time, events at points, influences propagating along world lines, geometry doing the work of gravity. Quantum mechanics is formulated in Hilbert space, an abstract mathematical structure where the state of an entangled system cannot be decomposed into separate states for each particle no matter how you try. The two theories are not just numerically incompatible when applied to the same regime. They describe the world using concepts that do not translate into each other. This has pushed a growing number of theoretical physicists toward a question that would have seemed extravagant 20 years ago. What if space-time itself is not fundamental? What if the smooth, continuous geometry of general relativity is not the basic structure of reality, but an emergent description that arises from something else? The candidate for that something else, in several lines of active research, is quantum entanglement. The ER equals EPR conjecture, developed by Juan Maldacena and Leonard Susskind in 2013, proposes that an entangled pair of particles is connected by a wormhole, a geometric bridge through spacetime, and that entanglement and geometry are two descriptions of the same underlying structure. If this is correct, spacetime is woven from correlations, not the other way around. Related ideas appear in the holographic principle and in tensor network models of spacetime, where the geometry of a region emerges from the entanglement structure of degrees of freedom on its boundary. These are not established results. They are conjectures, frameworks, research programs operating at the frontier where quantum mechanics and general relativity run out of reliable guidance. But the direction they all point is the same, toward a picture in which the separation between distant things, the very fact that here and there are different places, is not a primitive feature of reality, but a consequence of deeper quantum structure. Some physicists now suspect that entanglement is not a feature of spacetime but its source, that the smooth geometry of space and time we experience emerges from a deeper fabric of quantum correlations, which would mean that the most familiar feature of physical reality is not fundamental at all. At some point in the mid-20th century, the professional community of physicists arrived at an unofficial consensus. Stop asking what quantum mechanics means and start using it to calculate things. The attitude did not appear from nowhere. Quantum mechanics had produced results so spectacular, so relentlessly confirmed by experiment, that continuing to argue about its foundations started to feel like an indulgence the field could not afford. The theory predicted the magnetic moment of the electron to 11 decimal places. It explained the periodic table, the behavior of semiconductors, the structure of chemical bonds, the mechanics of nuclear reactions. Every time someone built an experiment to test it, quantum mechanics was right. The implicit lesson was difficult to argue with. Whatever the theory was describing at a philosophical level, it was obviously describing something real, and the most productive use of a physicist's time was to keep using it rather than to keep questioning it. This is where the phrase itself entered the culture. The instruction to shut up and calculate, a phrase often attributed to David Mermin, though he later distanced himself from it, captured an attitude that was already pervasive long before anyone put words to it. Asking what the wave function physically represents, asking what actually happens during measurement, asking whether the Born rule is derived or assumed, these questions began to carry a faint professional stigma. They were classified, implicitly and sometimes explicitly, as philosophy rather than physics. Funding went elsewhere. Graduate students were quietly steered toward problems that produced papers rather than headaches. What this culture suppressed, over decades, was the recognition that these were not merely philosophical questions. They were questions with direct consequences for the development of the theory itself. When physicists disagree about what a quantum state represents, they disagree about what quantum gravity should look like. When there is no consensus on what constitutes a measurement, there is no principled framework for understanding where quantum behavior ends and classical behavior begins. These gaps do not stay neatly contained in the foundations. They propagate outward into every frontier where quantum mechanics is being pushed into new territory. The surveys of professional physicists make the situation concrete in a way that is difficult to dismiss. When researchers have asked working physicists which interpretation of quantum mechanics they accept, no interpretation commands a majority. Copenhagen adjacent views draw the largest plurality, but only a plurality. Many worlds attracts a substantial fraction. Pilot wave theories, relational interpretations, and various other positions account for the rest, with a significant portion of respondents indicating genuine uncertainty or deliberate agnosticism. What this means is that the professional community has been operating for decades under a shared mathematical framework while holding fundamentally incompatible beliefs about what that framework describes. The calculations converge. The metaphysics fractures in every direction. The World Science Festival made this visible in a way that a survey table cannot quite capture. When Brian Greene assembled several of the field's most respected quantum theorists on a single stage and asked them to explain what happens during a quantum measurement, the panel did not converge on a single answer. Each physicist gave a different account, not different emphases on the same core idea, genuinely different accounts built on incompatible assumptions, leading to incompatible conclusions about the nature of reality. The audience was watching experts in one of the most mathematically precise sciences in human history openly disagree about the meaning of their own central process. This was not a debate about an unsettled frontier question. This was the basic mechanism of the theory, the thing that every quantum mechanics textbook introduces in the first few chapters, and there was no consensus to be found. The cost of this disagreement is not abstract. Quantum computing engineers designing error correction protocols need to understand how and when quantum coherence is lost, which is a question the measurement problem sits directly inside. Physicists attempting to construct a theory of quantum gravity need to know whether the wave function is a real physical object or a computational tool, because the answer changes the entire architecture of any unified theory. The decision to treat foundational questions as professionally marginal did not make those questions go away. It deferred them until the moment they became unavoidable, and that moment has been arriving from multiple directions simultaneously. There is something deeply strange about a field this rigorous tolerating this level of foundational ambiguity for this long. The consensus to stop asking was never formally adopted, never voted on, never written into any statement of scientific principle. It spread through the culture of graduate training, through grant priorities, through the implicit signal that papers about the interpretation of quantum mechanics would not appear in physical review letters. Generation after generation of physicists learned the formalism, learned to apply it with extraordinary skill, and learned not to press too hard on what lay beneath it. The remarkable predictive success of quantum mechanics became, paradoxically, the main obstacle to understanding it. The theory worked so well that questioning its foundations started to feel like ingratitude. For most of the 20th century, the measurement problem could be treated as an abstract philosophical concern that had no bearing on anything a physicist actually needed to do. Quantum computing ended that arrangement. The transition was not gradual. For decades, quantum mechanics was used to calculate energy levels, predict chemical reactions, and design semiconductor devices. And in all of these applications, the measurement problem stayed safely in the background. You ran your calculation, you got your number, you compared it to the experiment. What the wave function was actually doing, whether it collapsed or branched or dissolved into decoherence, was irrelevant to whether the answer matched the data. The foundational questions were genuinely optional in the sense that ignoring them cost you nothing. Quantum computing changed the terms of the arrangement in a specific and practical way, because a quantum computer does not merely use quantum mechanics to predict things. It uses quantum mechanical superposition as a computational resource, and then it measures. And the measurement is not incidental to the process, but is the process. Consider what a quantum computer actually does. A system of qubits evolves as a superposition of an exponential number of computational states simultaneously, and then at the end of the calculation the system is measured, collapsing that superposition to a single definite result. The entire computational advantage depends on maintaining the coherence of that superposition for long enough to extract something useful from it. Every interaction with the environment, stray electromagnetic fields, thermal vibrations, neighboring particles, constitutes a measurement in the relevant sense, collapsing the superposition prematurely and destroying the calculation. The engineers building these machines must therefore make precise decisions about what counts as a measurement and what does not, and the foundations of quantum mechanics, after a century of work, have not provided a precise answer to that question. Decoherence theory tells you that environmental interaction scrambles quantum phase relationships. It does not tell you exactly where the line is between an interaction that constitutes a measurement and one that merely nudges the system slightly. At small scales, this ambiguity was manageable. Early quantum computers operated on a handful of qubits, and the behavior was well described by standard quantum formalism without pressing too hard on interpretive questions. But laboratories are now operating at scales that were unimaginable even 15 years ago. IBM has crossed into what its researchers describe as utility scale, systems performing computations that classical machines cannot efficiently replicate, operating on processors with enough qubits that the classical simulation of their full quantum state is genuinely intractable. Google's Sycamore processor generated headlines when it completed a specific sampling problem in minutes that would have taken classical supercomputers thousands of years. At these scales, the intermediate behavior of the system, the point at which it transitions from behaving quantum mechanically to producing classical output, is not a textbook abstraction. It is a design parameter that determines whether the machine works. The classical quantum boundary, which introductory courses treat as obvious and sharp, becomes genuinely unclear when you are operating a device with hundreds of interacting qubits, applying error correction protocols that themselves involve measurement, and trying to characterize noise sources that blur the distinction between unwanted decoherence and wanted signal extraction. Error correction in quantum computing requires measuring the system frequently enough to detect errors without collapsing the quantum information you are trying to protect. This is a direct engineering instantiation of the measurement problem. You are asking, in hardware, the question that Bohr and Heisenberg left philosophically open. What constitutes an observation that destroys superposition, and what does not? He answers that current quantum engineers use are functional and approximate, derived from decoherence theory and empirical calibration, not from any resolved account of wave function collapse. What is emerging at the frontier of these experiments is something the standard formalism handles awkwardly, a regime in which systems are neither small enough to be fully quantum nor large enough to be fully classical. Wojciech Zurek's quantum Darwinism proposes that classicality emerges when information about a system proliferates redundantly through the environment, allowing many observers to agree on outcomes. This is a genuine insight, but the threshold at which this proliferation becomes sufficient for classical behavior to emerge, and the mechanism by which one outcome rather than another becomes the recorded result, remains theoretically unspecified at the level of precision that quantum hardware now demands. The gap between what the foundations say and what the engineers need is no longer a matter of philosophical taste. The question of what happens when a quantum system is measured, which textbooks handled by drawing a line between quantum and classical and forbidding questions about the line itself, is now an engineering problem that multi-billion-dollar laboratories are paying people to solve. There is one more thing wrong with the measurement process in quantum mechanics, separate from everything discussed so far. It is irreversible, in a theory that is otherwise not. Every equation governing quantum systems before measurement operates with complete indifference to the direction of time. Run the Schrödinger equation forward, and it describes a superposition spreading through all available possibilities. Run it backward, and the mathematics remains equally valid, equally precise, equally well-behaved. The fundamental law that governs quantum evolution contains no preferred arrow, no distinction between past and future, no mechanism that would allow the universe to tell the difference between the two directions. And yet the moment a measurement occurs, something changes permanently. A definite outcome appears, the superposition vanishes, and there is absolutely no procedure, mathematical or physical, that reverses the process and returns the system to what it was before. This asymmetry is not subtle. In every other domain of quantum theory, time reversal symmetry holds with extraordinary exactness. Particles interacting, fields oscillating, probabilities evolving, all of it runs equally well in either temporal direction. The mathematics has no concept of before and after in any fundamental sense. But measurement introduces an irreversibility so absolute that it looks categorically different from everything else the theory describes. Whatever happens during collapse, it produces a final state from which the prior state cannot be reconstructed. The information about which superposition existed before measurement does not survive measurement. It is not hidden in the environment, waiting to be recovered. It is simply gone, in a way that the Schrödinger equation itself cannot account for and does not predict. Consider what this means in the context of the broader problem. Physics at every level, classical mechanics, electrodynamics, general relativity, is built on laws that are time-symmetric or nearly so. The deep equations governing the physical world do not distinguish past from future, and yet the universe has a clear and undeniable arrow of time. Entropy increases, broken glass does not reassemble, Heat flows from hot objects to cold ones and not the reverse. The past is fixed and the future is open. Physicists have struggled for over a century to explain where this directional asymmetry comes from in a universe governed by time-symmetric laws, and the standard answer involves the extraordinarily low entropy state of the early universe, rather than any asymmetry in the fundamental equations themselves. Quantum measurement presents a different and more troubling version of the same question. Here, the irreversibility is not statistical, not a matter of overwhelming probability, not an artifact of initial conditions. It appears to be absolute. The collapse of a wave function does not simply make the reverse process improbable. According to standard quantum mechanics, the reverse process is not described anywhere in the theory. The formalism contains no mechanism for uncollapsing a wave function, no equation governing the transition from a definite outcome back to a superposition. What was indeterminate became determinate, and the mathematics provides no route back. This is not the probabilistic irreversibility of thermodynamics. This looks like a genuine one-way door built into the structure of the theory. What makes this especially strange is that nobody placed it there deliberately. The Schrödinger equation was not designed to produce irreversible measurements. The Born rule, which tells you the probability of each outcome, was added to the theory because it worked, not because anyone derived it from deeper time-asymmetric principles. The irreversibility of measurement emerged from the combination of these rules as an unexplained feature, sitting in the foundations of the most precisely tested theory in science with no derivation and no justification, resisting every attempt to trace it to something more fundamental. If quantum measurement is where the arrow of time is actually inserted into physical reality, if this is the mechanism by which the universe acquires its sense of before and after, then that mechanism is entirely unknown. The theory that cannot explain what a measurement is also cannot explain why measurements run in only one direction, why the act of observation leaves a permanent record, why the past crystallizes out of quantum indeterminacy and refuses to dissolve back into it. The Schrödinger equation works identically run forward or backward through time. But the moment a measurement occurs, the superposition is gone and cannot be recovered, and nothing in the mathematics explains why this should be so. After a century of quantum mechanics, after Bell's theorem and aspects experiments, and Wigner's friend and decoherence and many worlds and 100 variations on each, the situation is roughly as follows. The measurement problem remains unsolved, not partially solved, not solved in principle with details to be worked out, but genuinely, foundationally unresolved in a way that the field has collectively agreed to treat as acceptable. A quantum system evolves through superposition according to the Schrödinger equation until a measurement occurs, at which point one outcome appears and the others vanish, and the theory provides no coherent account of why this happens or what physical process produces it. This has been true since 1926, and it remains true now. The interpretations that have been proposed to fill this gap each demand a price that is, depending on your philosophical tolerance, either modest or enormous. Copenhagen declares that physical properties do not exist prior to measurement, that position and momentum and spin are not features of the world, but outcomes of interactions, and that asking what the particle was doing before you looked is not a meaningful scientific question. This works mathematically. It works extraordinarily well. It requires abandoning the intuition that there is a real world out there with definite properties proceeding independently of whether anyone observes it. Many physicists accepted this price immediately and never looked back. Many others found it unbearable and kept searching. Many worlds accepts the Schrödinger equation without modification and follows its consequences without flinching, which means accepting that every quantum measurement that has ever occurred caused the universe to branch into multiple copies, each containing a different outcome, all of them equally real. The mathematical elegance is genuine. The ontological cost is an uncountable proliferation of parallel worlds spawned at every quantum event throughout the entire history of the cosmos, none of which can ever interact with or be detected by any other. The probability problem alone, why certain outcomes appear more frequently than others if every outcome occurs, has generated decades of attempted solutions, none considered definitive. Decoherence, the approach most working physicists now default to when pressed, explains why macroscopic superpositions are never observed, why the quantum world transitions into something that looks classical at the scales of everyday experience. This is a genuine contribution, and it brought real clarity to questions that had seemed permanently obscure. It does not solve the measurement problem. After decoherence, the combined system of particle and environment is still technically in superposition, an enormously complicated superposition distributed across trillions of particles, impossible to observe in practice, but present in principle. The specific outcome still has no explanation. Decoherence transforms the problem without eliminating it. Objective collapse theories modify the equations themselves, proposing that spontaneous physical collapses occur at rates too small to detect for individual particles, but cumulatively fast enough to produce definite outcomes for macroscopic objects. These theories are testable in principle and falsifiable in ways that some interpretations are not, which gives them a scientific character the others sometimes lack. They require the introduction of new physical constants with no derivation from any deeper principle, and they remain incompatible with special relativity in their current forms, which is not a minor inconvenience. Below all of this sits the larger incompatibility that the measurement problem cannot even begin to address. Quantum mechanics and general relativity, the two frameworks responsible between them for essentially all of modern physics, are built on assumptions that contradict each other at the foundational level. Quantum mechanics requires quantized, probabilistic, non-local behavior at small scales. General relativity requires smooth, deterministic, local geometry at large ones. String theory has been attempting to bridge this gap since the 1980s without producing a confirmed experimental prediction. Loop quantum gravity has been attempting it nearly as long with similar results. The technology built on quantum mechanics works. The transistors work, the lasers work, the MRI machines work, the quantum computers now being assembled in laboratories around the world work within the limits imposed by decoherence and measurement error. The theory that underlies all of this operates at a precision that exceeds every other scientific framework in history. None of that resolves what the theory actually means, what it is describing when it evolves a wave function through superposition, or what occurs during the instant of measurement. These questions have been open for 100 years and are not measurably closer to resolution than they were when Bohr and Einstein argued about them at the Solvay conferences in the 1920s. The universe has arranged itself so that its deepest workings can be calculated to extraordinary precision and cannot, so far as anyone can tell, be understood at all.